my name is Daniel Stein, and today I'll be presenting the Charged Tape Lab. The purpose of this lab was demonstrate electrostatic forces using clear tape. By charging the tape, we could observe how it behaved with other pieces of tape and even with neutral objects. Our main goal was to estimate the net excess charge on the piece of tape using Coulomb's law and comparing the electric force to gravity. We calculated the tape carried about 3.3 times 10 to the negative 9 coulombs, and that corresponded to a transfer of roughly 2.06 times 10 to the 10 electrons. For the setup, we kept it simple. We used a roll of clear tape, a ruler, and post to drape the tape over. We charged the tape by ripping it off a base layer, and to prevent neutralization, we only held the non-sticky ends. When charged, the tape either repelled another piece of tape or floated slightly. This shows the balance between electrostatic and gravitational forces. Here's a diagram of the setup and the forces. It shows how the upward electrostatic force can balance the downward pull of gravity. This equilibrium is what allowed the tape to hover and why we could apply Coulomb's law to calculate its charge. As you can see here, this is the free body diagram, which shows the equilibrium, and the mass and the distance was really important for calculating Coulomb's law. We ran 3 trials and measured things like the tape's length, mass, distance apart, and room humidity. The numbers we chose were close but not identical, which showed small variations between each trial. From the data, we asked a few key questions. How consistent are the results? How much does humidity affect the charge? Do assumptions match reality? And how large is the charge compared to the total number of atoms in the tape? To simplify the math, we assumed each tape behaved like a point charge, that the charge was spread evenly, and that there was no air resistance. In reality, errors could come from handling the tape and accidentally neutralizing it, from small mistakes in distance measurements, and from environmental factors like humidity. Our model predicted the charge on the tape by setting the electric force equal to gravity. The result was about 3.3 times 10 to the negative 9 coulombs. This experiment confirmed the tape was strongly affected by electrostatic forces, but the actual behavior had more complexity than our model captured. Real life includes many more factors than our simplified math did. Here are our calculations. On the left-hand side, we have our variables initialized, and on the left side, or right side, this is the actual calculation. So this is a charge on the tape B, number of electrons, fraction of atoms that gain lost electrons, the gravitational force on tape B, and the area. These are our final values. The gravitational force on the tape was about 3.92 millinewtons. The excess charge was 3.3 nanocoulombs, equal to about 20 billion electrons. When compared to the total number of atoms, only 1 in about 10 million atoms on the tape surface was actually involved in a charge transfer. That's a very tiny fraction, but it still produced a noticeable force. To double check the math, I used GlowStrip to model the experiment. The code calculated was the electrostatic force and confirmed the values we found by hand. This gave us confidence our results were accurate. So basically, this is the point charges, and up is electrostatic force, down is the force of gravity, and right here, this code was basically just inputting the math of electrostatic force and the force of gravity. We used Lab1, which introduced the point charges and the arrows that told us how to make the point charges and the arrows, and basically all we did was we used our old electric field function, and we just basically we made some new values: gravity, mass, separation distance, force of gravity, and we calculated the electric force, for example the gravitational force vector, which was down, and the required charge to balance gravity. And then we calculated it, and we made the arrows into the positive and the negative. Our observation matched what we know about electrostatics. Like charges repel each other. Neutral objects were attracted because of polarization, where the charged tape pulled charges apart inside the neutral material. The hovering happened with the upward electrostatic force between the downward pull of gravity. One key insight was that a very small number of atoms needed to exchange electrons for us to see a strong electrostatic effect. To wrap it up, this experiment showed how strong electrostatic forces can be compared to gravity. The tape carried about 3.3 nanocoulombs of charge, which equals about 20 billion electrons. Even though this charge can come from just a tiny fraction of atoms, it was still enough to overcome gravity and move the tape. Overall, the lab demonstrated the power of electrostatic forces and how we can measure them with a single piece of tape.